Hello everyone. In this video we're going to keep doing what we've already started. We've done the binary relations on the last video. So what I've been doing as of late, well, just recently anyway. I've started using Notion. It's a pretty solid tool, to be honest, and I thought this would keep things organized for me. I mean, instead of me using one big sheet, I'll just use these, organize these under different topics, and then it will be easy to, revisit any of these topics. Like, for example, I got the sets here, and it still needs some work. I need to do lots of cleansing here, and but it's work in progress, bit by bit. No, I'll still keep the Google Doc anyway, just to, have all the information collected in one place and then organize things. It serves both as an organizational method as well, a management method, personal management method, and as well as a revising opportunity. Given you'll be moving data about, you'll have to revisit each and every bit of it. Anyways, so the last time we talked about the slopes, and then when we revisited the book, it was the talk was about partial ordering and bounds. Well, the bounds we've already know about those, but the problem is with given Zons lemma has been introduced here, and the series of videos that we've been visiting basically introduced us to up until binary and then linear functions. So the last topic was we've done the scatter plots, and we've done the functions, the slope and all. So this was the last video, linear equations, y equals mx. But we still have to go through slope intercept form. Yeah, let's do that now, and then decide on what we should do next.
Welcome to YU. In the last lecture, we introduced functions whose graphs in the Cartesian plane are lines passing through the origin. These are called linear functions and can be represented by the linear equation y equals mx, where m is a constant whose value can be any real number, positive, negative, or zero. The slope of a line described by this equation is determined by the value of m. Depending upon m, the slope can be positive, negative, or zero.
1 second.
Origin. Introduce functions whose graphs in the Cartesian plane are lines passing through the origin. These are called linear functions.
So linear functions. So to quickly revisit this, what we've said the last time. Just to, let's do a really quick recap on what we've studied the last time. So we've got on the binary relationships, there's something that differentiates binary relations from equivalence relations, and that is the symmetric and antisymmetric parts. So the antisymmetric parts means that if R relation with B is R related with B, then you can't go like B is R related to A. That would make, if that's the case, then it's called an equivalence relation given to other properties as sufficed, which is the reflexivity and association as well. But primarily with binary relationship, with binary relationships, they are antisymmetric. And this is what and there is something we should note, that there is also asymmetric. So there is antisymmetric and there is asymmetric. So we should differentiate those two terms as well. But for now, let's there is a note down below on what's the difference, but let's go through that for now. Let's go through that now. If a property is not symmetric, antisymmetric, then there can be one arrow or two. Example, if I like someone, then they may or may not like me. Either case could be true. If a property is asymmetric, then having one arrow means that there definitely cannot be two. If someone is my parent, they definitely cannot be their parent. So basically, that's the difference between antisymmetric and asymmetric. So antisymmetric, there could be a relation that that allows the symmetric to happen, but there are cases that are anti. As far as symmetric, there is no way that A related to B allows B to be related to A, or related to A. So basically, the difference between non-symmetric and asymmetric is that in one we might have two arrows some of the time, but in the other we can never have a second arrow once we have the first. Oh yeah? Yeah. Now, for the binary relation, it has to be, is it antisymmetric, or, because, if you take, the binary relation can happen on the same set, and if you have the same set, it depends on the relation. So, say for example, equals to, or bigger than, bigger or equal. If you have 1 bigger than or equal to 2, you can say 1 is bigger or equal to 1. This is sufficed. Let's do a quick Google. What's binary relation? Relation is neither symmetric nor symmetric, nor antisymmetric. I thought it was the relation empty set, but the answer in the textbook I'm using does not mention this as a possible answer. I don't understand why it can't be the answer. Could anyone explain? For a relation R to be symmetric, every ordered pair AB in R will also have BA. Yeah. For a relation to be asymmetric, you can't have, does not have this relation. For relation to be asymmetric, if both A and B and B and A are in R, then A equals B. So we want R such that for some A does not equal B, are both in R. This makes sure R is neither asymmetric nor antisymmetric. 1 city such that DZ does not belong to R, as this will ensure that R is not symmetric. In this case, we need witness in order to prove that it's not asymmetric, it cannot be empty. The grueling details of writing down such are for you. Oh boy, this is really interesting. Like, you need to prove each and every one of them. So basically it would depend, the answer for us here is that it would depend on the type of relationship that we have. It definitely would depend on the type of relationship we have. So if the relationship allows symmetric to happen, set A, B, C. Then we have A, B, A, C, and C, A. Okay, R is not symmetric because A related to B is true, but B related to A is false. R is not symmetric, is not asymmetric because ARC and CRA. R is not antisymmetric because ARC I think this condition would have been mentioned here, otherwise this one suffice, the last one. But I see where this is really going. This is should add this to the list of information we have here. So by the origin, and then we have a relation to B right, so that's that. And then let's go back to the summary. Yeah. Okay. A binary relation, antisymmetric or antisymmetric. It can also be called the graph, since you can graph it if it's in numbers in 2 dimensions. Binary selector. So I'm saying here that I mentioned here that it's antisymmetric. I'm not sure why I wrote this, but clearly there could be instances where, say, antisymmetric, it means that if A equals B, then the symmetric property is sufficed. Okay. Alright. It can be symbolized using A R related to B. So you can say A is R related to B, where A belongs to A and B. Yeah. Binary relation is always a subset of the Cartesian product. Yeah. So the binary relation is a subset of the Cartesian product. Usually the Cartesian product contains more ordered pairs or pairs. Binary relation can exist on the same set. Just keep in mind order matters. Binary relation in the same set can be denoted by A R related to A, like A being Bob and another being Alice. Then R could be older, so B is older than Alice. The R relation is in the same set. Yeah, there are no duplicates in sets, of course. Sometimes plotting binary relation in a graph takes up a small portion. Yeah, sometimes when you do graph, you have a set of data and you graph them and you plot them on a graph. It may look like the data is condensed in a small, like to the side. Then in that case, you could just expand the graph or zoom the graph to that area, rendering 0, 0 to be hidden. Like in these graphs here, you can see that the starting point is 60, This is just to zoom on the data that we have here. And as you see the data is plotted, you could create this, what you call best fit, the line of best fit, or the correlation line. So given the data is closely located to the best fit line, this means that it's a positive correlation, and the strong correlation relation, the strong relation here, given these these data points are quite close. If it's on the other direction, then you say it's a negative correlation. If there's no line to be drawn, then you can't really say it's correlated. And there's something else you should consider, and that is this is very important, because the way that you draw this line is, there are several methods to actually draw this, but one of the common methods or the algorithms is called the least squared. So you basically calculate the vertical distance from the point to the closest center, or I'm not really sure how it's done, but I feel like, if I'm not mistaken, it's the vertical distance to the next closest point, I think. I'm not really sure, but we can explore this as we dive more into linear algebra. Anyway, so let's keep going. I've already talked about the and then we talked about the symmetric and asymmetric, so we passed those. And then we have the linear functions. The linear functions usually pass by the origin, and then you have m being basically the magnitude of the slope. The larger the number, the closer it hits to the y-axis, and the smaller the number, the closer the less steeper the slope would be. So that's that. So let's do the video now.
Can be represented by the linear equation y equals mx, where m is a constant whose value can be any real number, positive, negative, or 0. The slope of a line described by this equation is determined by the value of m. Depending upon m, the slope can be positive, negative, or 0. However, all graphs described by equations of this form are lines which pass through the origin. In this lecture, we will introduce linear functions whose graphs do not pass through the origin. These functions are sometimes called affine functions. The equation y equals x is a simple linear equation describing a line passing through the origin. Every point on this line has a y-coordinate whose value is equal to its x-coordinate. Now, if instead of equating y to x, we equate y to x plus 1, every point's y-coordinate will be 1 greater than before. Every point on this line has a y-coordinate whose value is 1 greater than the value of its x-coordinate. This equation describes the same line as before, but the entire line is 1 unit higher on the Cartesian plane. Likewise, the equation y equals x plus 2 describes a line 2 units higher.
I just need to check if the affine functions are a type of linear functions, or linear functions are only those that pass by the origin. Okay, so apparently they are. So affine functions are type of linear function. Linear function plus a constant. Constant. It is when the line does not pass by the origin. So you get y equals x plus, I don't know, c. Yeah, so then we could see this question here real quick. I'm a bit confused. What's the difference between a linear and a affine function? It's linear if those notations are really weird. This is 110 replies. Damn, that's good. A linear function fixes the origin, whereas an affine function need not do so. An affine function is the composition of a linear function with a translation. So while a linear part fixes the origin, translation can map it somewhere else. Linear functions between vector spaces preserve the vector space structure. So in particular, they must fix the origin. Does not preserve the origin. Okay. Pass by the origin. Functions, linear function plus a constant. So they're not really a type of linear function. It's more like it is it's a different type of function that allows the creation of a whole new different thing. Okay.
Or the equation y equals x minus 2 describes a line 2 units lower. In general, adding any real number b to the right side of this equation will shift the graph up or down by b units. This is true for other linear equations as well. For For example, if we start with the equation y equals 2x and add 3 to the right side of the equation, the graph will be shifted up by 3 units. Once again, this is because the y-coordinate of every point on the graph is 3 units greater than if we had not added 3 to the right side of the equation. For this same reason, taking any linear equation of the form y equals mx and adding a constant b to the right side shifts the graph vertically by b units. The graph is shifted up if b is positive, or down if b is negative. This shifting of the graph is referred to as a translation. We say that the graph has been translated vertically by b units. The value of b determines the point at which the graph crosses the y-axis. This point is called the y-intercept. The y-intercept has coordinates 0, b. The first coordinate of the y-intercept is always 0, because every point on the y-axis has an x-coordinate of 0. Since we know that x is 0, we can find the y-coordinate by making the value of x 0 in the equation. This makes the first term in the equation m times 0, which is just 0. So the first term goes away, leaving us with the equation y equals b. Therefore, when x is 0, y must equal b. This tells us that the graph of any equation of the form y equals mx plus b always has a y-intercept with the coordinates 0, b. Because the constants m and b determine the slope and y-intercept, this form of the equation of a line is called the slope-intercept form. And any non-vertical line can be described by this equation. By adjusting the values of the constants m and b, we can orient the line in any way that we like. The value of b determines the line's vertical position, and the value of m determines the line's slope. Together, these two constants determine the orientation of any non-vertical line in the Cartesian plane. In the next lecture, we will show how to calculate the value of a line slope, m. Mohawk, and welcome to YU. In the last lecture, we saw how an equation for a line can be written in slope-intercept form.
There are many dislikes here. Let me explore what's the deal here. Alright, there's nothing interesting in the comments, so I'm not sure why there are many dislikes here, but let's see.
This form of a linear equation is written as y equals mx plus b, where x is typically chosen as the independent variable, y is the dependent variable, and m and b are constants. We saw that the constant b determines the point at which the line intersects the y-axis. This point is called the y-intercept, and its coordinates are 0, b. We also saw that the constant m determines the slope of the line. But what exactly is slope? The slope is a number which specifies how much a line is tilted from the horizontal position. The sign of the slope indicates which way the line is tilted. A positive slope indicates that the line's elevation increases as we move to the right. And a negative slope indicates that the elevation decreases moving to the right. The magnitude of the slope is determined by the amount of change in the line's elevation over one horizontal unit of distance. The greater the change in elevation over 1 unit distance, the greater the slope. This mathematical concept of slope corresponds to our experience in everyday life. A level road has a slope of 0. A road with a small slope changes elevation a small amount every kilometer. A road with a larger slope changes elevation by a larger amount in the same distance. Likewise, the slope of a line is defined as the number of units by which its elevation changes as we move 1 unit to the right. For example, if when moving 1 unit to the right, the line's elevation increases by 1 unit, then the slope of the line is 1. If the elevation increases by 2 units, the slope is 2. Likewise, if when moving 1 unit to the right, the elevation decreases by 2 units, the slope is negative 2. The elevation of a horizontal line doesn't change regardless of how we move, so its slope is 0. When calculating slope, the type of units used to measure distance does not matter, as long as we use the same units to measure both the horizontal and vertical distances. Using this definition for slope, we can determine the slope of a line by examining any 2 points on the line which are separated by a horizontal distance of 1 unit. Since the slope of a line is the same at every point, the 2 points we choose can be located anywhere along the line, as long as the points are separated horizontally by exactly 1 unit. The slope is simply the change in elevation as we move from the left point to the right point. Since the y-coordinate of a point represents its vertical position, the difference in elevation is the y-coordinate of the right point minus the y-coordinate of the left point. This difference in y-coordinates, as we move 1 unit to the right, is the line's slope. To see how this works, let's find the slope of the graph of the equation y equals x. We start by picking a pair of points on this line separated horizontally by 1 unit. For instance, we could pick the points 3, 3 and 4, 4. The right point of this pair has a y-coordinate of 4, and the left point a y-coordinate of 3. The elevation difference is the y-coordinate of the right point minus the y-coordinate of the left point, which gives us 4 minus 3, or 1.
I should write this down. So, in order to calculate the slope, take any 2 points on the line. Example, take like, I don't know, so it's 3, 3 and 4, 4. Notice 1 unit apart. Oops. X-axis. Taking the y coordinate values, we get 4 and 3. Subtracting those leads to 1, and that is slope. In order to reduce the confusion here, we could take, I don't know, 92 points. We could like gone. Yeah, it would have changed the slope, right?
So the slope of this line is 1. Now let's find the slope of the line y equals negative x. Once again, we can pick any 2 points separated horizontally by 1 unit. If we pick the points 3, negative 3 and 4, negative 4, the right point's y-coordinate is negative 4 and the left point's y-coordinate is negative 3. So the right point's y-coordinate minus the left is negative 4 minus negative 3,
Negative 1.
which is the same as negative 4 plus 3, or negative 1. So the slope of this line is negative 1. So far, we have picked 2 points with a horizontal separation of 1 unit. But what if we want to calculate the slope using 2 points which are separated by some other distance? We know how to calculate the slope of a line using a pair of points 1 horizontal unit apart. Since these points have a vertical separation of 2 units, the slope of this line is 2. But let's say we want to use 2 points on the line separated by a horizontal distance of 2 units. Now the horizontal separation is doubled. But notice that the vertical distance is also doubled. The vertical distance is now 4 units. Likewise, if we use 2 points with a horizontal separation of 3 units, the vertical distance is tripled to 6 units. This is because each horizontal unit adds the same change in vertical distance. Let's call the vertical distance between the 2 points delta y. The symbol delta is often used to indicate difference. This is appropriate since delta y is the difference between the points' vertical positions. Likewise, we call the difference in horizontal position delta x. If delta x is 1 unit, we know that delta y is the slope of the line. As we change the distance between the pair of points, both delta x and delta y change by the same multiple. If we change delta x by a multiple of 2 or 3, delta y also changes by that multiple. In general, if delta x is multiplied by any constant c, delta y will change by the same constant multiple c. Now, let's divide delta y by delta x. Since delta y is equal to c times the slope, and delta x is equal to c, delta y divided by delta x is the same as c times the slope divided by c, or simply the slope. This equality tells us that for any 2 points on a line, the difference in the y-coordinates divided by the difference in the x-coordinates is the line's slope.
Yeah, we should decide on how this conclusion
slope
was made. So, delta y
divided by c.
This is what you're looking for. We need to do this. Good. Assuming delta x is c, so delta y would equal c multiplied by slope. C's cancel each other, making the slope being the change in y over the change in x.
Or simply the slope. This equality tells us that for any 2 points on a line, the difference in the y-coordinates divided by the difference in the x-coordinates is the line's slope. This definition is simple but powerful. It is a definition which we will use many times in higher mathematics as well as in other branches of science and engineering. If we know the coordinates of any 2 distinct points on a line, we can use delta y over delta x to calculate the line's slope.
By the way, I mean, as we proceed down in linear algebra, in machine learning algorithms, much of the machine learning algorithms actually depend on this formula here. And yeah, just wait to see.
As an example, let's use this to calculate the slope for a line which runs through 2 points with coordinates 3, 3 and 7, 7. First, we calculate delta y and delta x.
It's 4 over 4.
As we saw before, delta y is the y-coordinate of the right point minus the y-coordinate of the left point. So delta y is 7 minus 3, or 4. Likewise, delta x is also 7 minus 3, or 4. So the slope y over delta x is 4 divided by 4, or 1. As a second example, let's calculate the slope for a line which runs through the pair of points 3, negative 3 and 7, negative 7. Once again, delta y is the y-coordinate of the right point minus the y-coordinate of the left point. This time, delta y is negative 7 minus negative 3, or negative 4. And delta x is 7 minus 3, or 4. So the slope, delta y over delta x, is negative 4 divided by 4, or negative 1. When using this formula to calculate a line slope, no matter which 2 points on the line we choose, we will always get the same answer. As an example, let's try calculating the slope for a line using several different pairs of points. Let's say that we know of 3 points which fall on this line. The points with coordinates 8, 5, 4, 3, and negative 6, negative 2. We will start by calculating the slope using the points 8, 5, and 4, 3. Delta y is the y-coordinate of the right point minus the y-coordinate of the left point, which is 5 minus 3, or 2. And delta x is the x-coordinate of the right point minus the x-coordinate of the left point, which is 8 minus 4, or 4. So the slope delta y over delta x is 2 divided by 4, or 1/2. Now, let's calculate the slope of the same line using a different pair of points. 4, 3, and negative 6, negative 2. Once again, delta y is the y-coordinate of the right point minus the y-coordinate of the left point, or 3 minus negative 2. Which is the same as 3 plus 2, or 5. And delta x is the x-coordinate of the right point minus the x-coordinate of the left point, or 4 minus negative 6, which is the same as 4 plus 6, or 10.
10 over 5.
So the slope, delta y over delta x, is 5 divided by 10, or 1/2. The same value we calculated before using a different pair of points.
So 2 pair of points suffice just fine.
Now let's calculate the slope one more time using the points 8, 5 and -6, -2. Once again, delta y is the y-coordinate of the right point minus the y-coordinate of the left point, or 5 minus -2, which is equal to 7. Delta x is the x-coordinate of the right point minus the x-coordinate of the left point, or 8 minus -6, which is equal to 14. So the slope delta y over delta x is 7 divided by 14, or once again 1/2. No matter which pair of points on this line we choose, the calculation for slope will always result in the same value. This makes sense since, as we saw, the equation for a line contains a single constant m whose value is the slope of the line. Since there is only one value for a line slope, a line must have the same slope everywhere no matter which 2 points are used in the calculation. As a general example, let's call the left point point 1 and the right point point 2. We will refer to the coordinates of point 1 as x1 and y1, and the coordinates of point 2 as x2 and y2. Now, delta y and delta x are y2 minus y1 and x2 minus x1. So the slope delta y over delta x is y2 minus y1 over x2 minus x1. This is the general formula for the slope of a line given any 2 points on the line with coordinates x1, y1, and x2, y2. Of course, this can also be represented as delta y over delta x. Sometimes the difference in elevation, delta y, is referred to as the rise, and the difference in horizontal position, delta x, is referred to as the run. So an easy way to remember this formula is that the slope is equal to the rise over the run. In the next lecture, we will use this formula for slope to create a different form of the equation for a line called the point-slope form.
So, this is basically what people were complaining about in the comments section. And that there was a weird introduction to the delta y's over delta. I don't know. It just sounded like it's a simple. I mean, the guy really did a really good effort in these videos, and it's really appreciated. All right, so that's that. I know I've said before in the beginning of the video we should resolve these before jumping into the graphs even deeper, because apparently we need to dive even more point slope form, and then we got all different goodies coming up ahead, and that's basically the core of linear algebra. Before we jump into those, I think we need to cover and we need to fully understand what these actually mean, partial ordering and all this stuff. Alright, so just leave this to the next video then. Cheers.